Our next two chapters, chapters 10 and 11, are going to be on trigonometry. Trigon means triangle. We call them triangles because they have three angles, but we could easily call them trigons because they have three sides. Decagon is a 10-sided shape. Polygon is an any-sided shape, so trigon is a three-sided shape. Trigonometry is trigon plus geometry. It's the geometry of triangles, basically. Really, this meter means measure. We're doing measurements and angles on triangles, trigonometry. In these two chapters, we'll make two chapters out of it. We'll start with right triangle trig. Most of your trig ratios deal with right triangles first, and then do any triangles. And then circle trig, which is what I call it, and that sounds like an oxymoron, but just stick with me. Then we'll graph trig functions, we'll simplify trig identities, and we'll solve trig equations. And those 6 main topics will be split up over several sections and videos. Let's talk about how we set up these triangles. Over here, we have a triangle. This is actually a right triangle because this corner here is a right angle. And just some basics to get covered. When we have a capital letter, we're talking about an angle, and the lowercase letter is the side. And ideally, the angle and the side are opposite. Meaning if this is angle A, then this down here is side A. We want them opposite each other because that way it's clear. You know, if we said it was the angle next to it, the side and the angle touched each other, then this could be side A or this could be side A. We don't want that, so the angle and the side are opposite each other. And the way that we say that is the word subtends. So angle A is subtending side A, which goes from C to B. In a right triangle, we typically have angle C be the right angle, which makes side C the hypotenuse. And we all wish we were high on hypotenuse, right? Okay.
Hey. See, the longest one.
I wish I were high on hypotenuse.
One of the 3 sides.
I wish I was high on hypotenuse.
Side A and B are the legs. In right triangles, you have a hypotenuse and you have legs. So there's 3 basic trig ratios. There's sine, which we abbreviate SIN, but don't ever call it sin. That is sine. Then we use this symbol theta. This theta means you have an angle. It's a variable. We could just as easily call it sine of x, but we like to use this theta, which is a Greek letter, to say you're talking about an angle. Whenever you have a theta, you know you're dealing with an angle. Sine is a ratio. It's the ratio of the opposite side over the hypotenuse side. So all of these sine, cosine, tangent ratios you're going to see today only apply to right triangles. Don't try to apply them to non-right triangles. We'll learn how to do things like that later. Don't call this cos, call it cosine. The cosine is the adjacent side divided by the hypotenuse. It's a ratio, two compared values being divided. And then tangent, don't ever call this tan, please call it tangent. The tangent of theta is the opposite over the adjacent. The thing that can be kind of tricky about this is that the terms opposite and adjacent are relative, meaning they change based on what you're talking about. So if I wanted to find the sine of angle A over here, well then if this is my theta, if this is angle A, sine of theta, then this side is the opposite. So the sine of angle theta would be side A over side C, because this is the hypotenuse. And the cosine of angle theta, if it's A, the cosine of A, well this is the adjacent side to this angle. So adjacent means it's the side touching the angle, but not the hypotenuse. The side that touches the angle but isn't the hypotenuse. So the cosine of A, of angle A, is side B over C. But these things change if I have a different angle. So now if I do B, well the sine of B is still opposite over adjacent, but opposite is now this. So the sine of B is B over C, whereas the sine of A was A over C. So whichever side is opposite or adjacent depends on which angle you're talking about. Sine of A, here's the opposite. Sine of B, here's the opposite. So you have to be aware of that level of relativity. Before we go on, I want to talk about what trig ratios really are. My guess is that you've used these before, so I'm not going to go into great detail about like how sine is opposite over adjacent. I want to talk about what's happening though, like where these come from and why they're useful. So I'm going to make a triangle, and this triangle is going to be have a height of 2 and a length of 4, width of 4 really. Oh, this just isn't quite right. It just popped off there, so I'm going to try that again. Please notice how what I have here is two number lines. A number line that's really the x-axis, and a number line that is really the y-axis. And that gives you a grid. I didn't draw the grid here, but these measurements are giving me like a coordinate plane with the x-y axis. Two number lines make up that plane. Well, this is a 2x4 shape. Let's make the inside of it white. Yeah, I'll keep it black. This will work. This is 2x4. I'm going to make another similar triangle. Similar meaning it's going to have the same shape, only it's going to have a perimeter that's twice as big. And for the record, when you double the perimeter, the area quadruples. It's a square. So if I were to ever triple the perimeter, then the area would get 9 times bigger. Well, this triangle is now, this is 2x4, and this one's 4x8. These two triangles are similar, meaning I could scale one to look like the other. If I took this triangle and put it here, come on, move with me, put it here, and then dragged this corner this way, oh shoot, I broke that. Undo that. I'm going to put it up here. If I put it up here, and I drag this corner this way, they're going to stay the same. They're the same shape, just a little bit off because I drew it by hand, so they're not totally perfect. But these are essentially the same shape, just with different size, and that makes them similar. Really, more importantly, is they share the same angles. These are both right angles, and we've seen how these two angles fit together. This angle here is going to match this angle here. The angles fit in that corner, and these angles fit down in the bottom right corner also, right down here I'm looking. Similar triangles, okay? A lot of work there to convince you that these two triangles are similar. Similar triangles have proportional side lengths. That means when this is 2 and this is 4, okay, that was a double relationship. From 2 to 4 was doubling. So if this is 4, this is 8. They have proportional side lengths. But what I could also do is check, how does this ratio here compare? This is the ratio 4 over 2. I'm going to take this side first. I'm going to do base to height. This is the ratio 8 over 4. Well, these are the same thing. They both just simplify to 2 over 1, or just 2. But it turns out this would be the case no matter how big these triangles were. Like I made them 2x4, but I could make it something else. Like let's say this is 1.7, then this would be 3.4. And that ratio, 3.4 over 1.7, would be the same as our 8 over 4, which is the same as our 4 over 2, which just gets us 2 over 1. That ratio will be true no matter how big these triangles are. If these triangles are similar, if these angles match and these angles match, then the ratio of sides is always going to be the same. So somebody one day, probably a few people, got together and they realized, you know, we know all these triangles are going to have the same ratio no matter how big they are. In fact, if we measure this angle is 64 degrees, and this angle over here is 64 degrees, well, we now know that if we took any angle that's 64 degrees, and we took this side here, which I'll call A, and this side here, which I'll call B, A over B will always equal the same thing. It'll always be 2. Well, let's write that down. Let's say, okay, if you have the opposite and you divide it by the adjacent of angle A, and you have a 64 degree triangle, that'll always come out to the ratio 2 over 1. So they wrote it down. And they did that for 64 degrees and 63 degrees and 62 degrees. And they cataloged every possible ratio of every possible triangle. And instead of calling it opposite over adjacent, they called it tangent. And we can talk about why that is some other time. Remember, a tangent is a term for a circle. A tangent is a line that barely touches the circle on the edge and is perpendicular to the radius in the middle. So it actually relates to that later on. We'll come back to that someday. Every triangle that's 64 degrees in that top corner angle will have the opposite over adjacent ratio of 2 over 1. And if I pull up my calculator, and in my calculator I type in the tangent of 64, I'm really hoping I get out a number close to 2. And the tangent of 64 is basically 2. The reason it was off is because this isn't exactly 64 degrees. It's just a little bit off from 64 degrees, but the computer's rounding for me. So they wrote down those ratios for every single possible triangle, And they did it for opposite to adjacent. They did it for opposite to hypotenuse, hypotenuse to adjacent, hypotenuse to opposite. They covered all of them. And they gave them all terms. So when you look up the sine of 34, well, if I do the sine of 34 in my calculator, and pre-calculator I would just pull up a chart, go to a table, and scroll through it. If I do the sine of 34, that means I get 0.559. What that's telling me is in any triangle with a 34-degree angle here, if this is 0.559 in length, then this over here is 1 in length. And that ratio is always going to be the same. So I could double this. This could be whatever 0.559 is times 2. Let's call it 1.02. I don't think it's that. I don't really care that much. And I meant 1.20. It's pretty close to that. Then this would be 2. The ratio won't change. And so they wrote all those down, and then they put them on a piece of paper. And then we eventually took them all and we put them in a calculator. So your calculator is pulling up the ratio of these sides for all the possible combinations of the triangles. Just to really try and bring this home.
6.5 hours later.
The cosine of 34. Cosine of 34 gives me 0.83. Okay, that means that if one side is 0.83, the adjacent side, if this side of this triangle over here is 0.83, then the hypotenuse over here is going to be 1. But if it was doubled, if this was 1.66, then this would be 2. The ratio is always going to come out to 0.83. On your calculator, please do this now. If you type in something like the cosine of 34 and don't get this, and you get some other number, press this mode button right here and go down and change your radians to degrees. We'll talk about what radians are later. We'll probably end up using them more than degrees as the class goes on. But for now, just have your calculator set to degrees and not radians. Okay, so let's keep going. There are reciprocal trig functions. Cosecant is the reciprocal of sine. That does not mean the inverse, it means the reciprocal. So cosecant is literally 1 over sine, which makes it hypotenuse over opposite. Secant is the reciprocal of cosine, literally 1 over cosine, so it's the hypotenuse over the adjacent. You put the hypotenuse side on top and the adjacent side on the bottom. And do you remember what a secant is? You probably learned about them in geometry. And what a secant is in geometry can come up again with what a secant is in trig. Can be kind of fun. Cotangent is the reciprocal of tangent. It's literally 1 over tangent, which makes it adjacent over opposite as opposed to opposite over adjacent. So there are actually 6 trig functions. Sine, cosine, tangent, cosecant, secant, cotangent. And it's kind of annoying that cosecant goes to sine. You wish that cosecant was the reciprocal of cosine, because it just feels like that would make so much sense. It's like, why didn't they make the cosecant the reciprocal of cosine? Well, because a secant is actually a thing. And so where the secant is coming from is from what it means in a circle. And secant actually just ends up relating to cosine. Because what you probably don't understand is how cosine and sine relate to each other. And this is kind of fun. I just learned this sort of recently. Cosine is the complement of sine. If you remember, complements are things that add up to 90 degrees or things that make you feel really good about yourself as a person. But in math class, there are things that add up to 90s. So 60 and 30 are complements of each other because they both add up to 90. Well, this makes perfect sense because in a triangle, these two angles, in a right triangle, these two angles are going to add up to 90. These two angles are complements of each other. So the sine of one is the cosine of the other because they're complements. You'll often see that the sine plus the cosine adds up to 90 because they're complements. So again, you wish secant went to sine, and you wish cosecant went to cosine, but it doesn't. So just do the annoying thing. Think, okay, it's not what I wish it was, it's the other thing, so do that. Cotangent going to tangent is actually pretty nice because that's fairly simple. So I'm told that sine of theta is 5 over 13, and I want to find the rest of the 5 trig ratios. So I know sine, but I want to find cosine and tangent, and I also want to find cosecant and secant and cotangent. And I have these written out in such a way that they're paired, right? Like sine goes to cosecant, cosine goes to secant with a C, secant, and tangent goes to cotangent. Here's my secant. Well, if the sine of theta is 5 over 13, we know that that's opposite over hypotenuse. So if it's 5 over 13, I'm not going to call any side, they're all going to be whole numbers. I don't want them to be fractions. So I'm going to make this my theta. I wasn't told what's what, so really I shouldn't have even drawn the triangle here first. Pretend like this triangle wasn't here, and I see just this. Then I'm going to go, okay, here's a triangle. I'm going to pick something to be theta, and I'm going to call this opposite, which makes this hypotenuse. I'll do that over here because the triangle's prettier. There's opposite and there's hypotenuse. Well, I need to have that third side length to be able to find cosine, or tangent, or cotangent. So I have to find this side length, which I'll call side B, because this would be A, and we'll call this B, so we'll call this C. So here I can just use Pythag. I know that A squared plus B squared equals C squared, and I'm calling my A value 5. I don't know my B value, but my C value is 13. So 25 plus B squared is 169. Subtract 25 from both sides, B squared is 144. So B is 12. You're supposed to do a plus or minus when you square root, but we're not going to have a positive and a negative length. It's just going to be a positive length, so don't worry about the negative. So this triangle is 12 and 5 on the legs and 13 on the hypotenuse. Well, now I can find everything really quickly. The sine we already have, it's 5/13. Cosine is opposite over hypotenuse. No, sorry, adjacent over hypotenuse. Cosine is adjacent over hypotenuse. So that's 12 over 13. Tangent is opposite over adjacent, 5/12. I'm just writing down these ratios, because all sine, cosine, tangent are ratios. Cosecant is 1 over sines, the reciprocal of sine, so it's 3/5. I just take this fraction and I flip it over. Secant is 3/12. 13, so 13/12. And cotangent is 12/5. Interesting to note that tangent and cotangent can be any number, but sine and cosine are always less than 1. Cosecant and secant are always greater than 1. And if you think about what it means to be sine, you'll know why that makes sense. But I'm not going to tell you why that is, because it's going to come up on a quiz later on. Maybe even a video quiz after this video. But sine and cosine are always going to be less than 1, which makes perfect sense if you just analyze it for a second. Let's keep going. Here's another example. Cosine of theta is root 2 over 11. Good. Here's one where I didn't draw the triangle. I'm just going to draw any right triangle. It doesn't matter what you pick theta to be, so this time I'll make this theta. Cosine is hypotenuse on the bottom and the adjacent side on top. So the adjacent side is root 2, the hypotenuse is 11. The question is, what's that side over there? So I'm going to do root 2 squared plus b squared equals 11 squared. So 2 plus b squared is 121. So b squared is 119. So b is the square root of 119. Just use Pythag. And now I can find everything real quick. Sine is opposite over hypotenuse, which is root 119 over 11. Cosine we already have. It's root 2 over 11. And tangent is opposite over hypotenuse, which is root 119 over root 2. Now, you might remember, we're not allowed to have radicals in the bottoms of fractions. So I'm going to rationalize this by multiplying by 1, by root 2 over root 2. Because root 2 times root 2 is just 2, and 119 times 2, so this becomes root 138. That is what I would call my tangent. You can't have radicals in bottoms of fractions, so rationalize. So then cosecant is next. I didn't leave myself a ton of room, but cosecant is 1 over sine. So cosecant of theta is going to be 11 over the square root of 119. But I'm not allowed to have radicals in the bottom, so I multiply by root 119 on top and bottom. And I get 11 root 119 over 119. If I could simplify any further, if the 11 and the 119 could cancel or reduce, I would do that, but it can't, so I don't. I'm going to switch colors. I don't really know why, but I felt like it. Cosine becomes secant. The secant of theta is going to be 11 over root 2, which becomes 11 root 2 over 2. You should get to the point where you can do this very quickly, this rationalizing. And then tangent is just going to flip over this fraction. You could flip over this fraction, but that's going to require some simplifying. I recommend instead you flip over this fraction here. So cotangent of theta is going to be root 2 over root 119. and I multiply the top and the bottom by root 119, and you'll notice that the bottom number is, of course, different here than it was in tangent. So it's root 238 over 119. You might be wondering, can root 238 break down? It looks like it's very breakdownable. Well, this number isn't even, and so 2 has nothing to pair up with. And I'm pretty sure 119 can't break down. I bet it's prime. If it's not prime, then it's very close to being prime. So, no. Sine, cosine, tangent, cosecant, secant, cotangent, written out in a very weird order. And you notice I even stopped looking at the triangle, but drawing up the triangle first to know what's opposite, what's adjacent, what angle you're talking about. Remember, I just could pick this angle to be whatever spot I wanted to be. I mean, it couldn't be here, but it could have been here if I'd wanted. And then set up your ratios. Okay, let's talk about inverses now. Inverse has been a major theme in this class. The question of what inverse means has come up several times. Inverse is how we undo things. It's the action of undoing something. So the inverse of addition is subtraction. They invert each other. The inverse of multiplication is division. They undo each other. The inverse of an exponent is a logarithm, which we talked about a couple chapters ago now. And the inverse of a trig function is called the inverse trig function. Sine, cosine, and tangent give you ratios of sides, okay? Sine, cosine, and tangent give you ratios of sides. Sine inverse, that looks like this, gives you the angle from the ratio. So if sine gives you a side length, sine inverse gives you an angle length. It's if you know the ratio, you can work backwards to find the angle. And remember how I talked about how sine was like a big list, where you'd put like some angle over here, and then over here you would have some ratio? Well, what we could do now is just look for the ratio first and go backwards to find the angle. It's like we're doing this on paper, but instead we can do it with our calculators or with some functions here. So for example, I know that theta is the angle I'm trying to find in this right triangle, and the opposite is 4 and the adjacent is 6. Sorry, that's the hypotenuse. The opposite is 4 and the hypotenuse is 6. Okay, so the sine of theta is 4 over 6, which can reduce to 2 over 3. So you might be asking, why did I use sine? Why didn't I use cosine or tangent or cosecant or something? Because I had an opposite and a hypotenuse. If I had an adjacent and a hypotenuse, I would have done cosine, because cosine is adjacent over hypotenuse. But I had an opposite and a hypotenuse, so I'm doing sine. If the sine of theta is 2/3, I want to find what theta is. So I'm going to take an inverse sine of both sides. The inverse sine of the sine of theta equals the inverse sine of 2/3. Well, now the inverse sine and the sine undo each other. They're inverses of each other. So theta is going to be, angle theta, the angle, the measure of the angle, is going to be the inverse sine of 2/3. Because we don't use the paper logs anymore, we're just going to do this in our calculator. If I do second sine, that's inverse. This right now is sine inverse. So the sine inverse of 2/3 is 41.8 degrees. Theta is 41.8 degrees. And if I know that theta is 41.8, this must be 48.2 because they have to be complementary. And notice, if I did the cosine of 2/3, cosine inverse, I get that 48.2 because they're complements. Cosine is the complement of sine. They're going to add up to 90. So we can do it again over here. Here I've got this angle theta. This is again the opposite, and this is again the hypotenuse. We just did opposite over hypotenuse. So let's do it this, ooh, I can't move that 9. It's all locked in together. Let's move the 9 over here. We'll call it 0.9 to make it shorter. So this is 5 and this is 0.9. This picture's not going to be to scale. I now know that the tangent of theta is opposite over adjacent. 5 divided by 0.9. Tangent of theta is 5 divided by 0.9. So theta is going to equal the tangent inverse of 5 over 0.9. I took a tan inverse of both sides. So my theta is now 79.7 degrees. This is going to be basically 80 degrees. Not exactly, but pretty close. I should do 79.8. I just really want to stress, sine, cosine, tangent of right triangles, those give you side lengths. They give you ratios of the triangle's sides. Sine inverse, cosine inverse, tangent inverse of right triangles, only right triangles, gives you angle measures. And one more thing to stress, if I do this, this is the inverse sine of 0.3. But if I do this, that is now cosecant. Okay? Sine to the -1 is the inverse. 1 over sine is the reciprocal, which we would call the cosecant in this case. So this is an this is a side ratio. This is an angle measure. 1 over sine and sine of the -1 are different things, and that's a bit confusing, but also kind of a bit not. Really, it could be this is inverse. I should write this better. This is inverse. Whereas this, what's a theta there? Sine of theta to the -1 is reciprocal. Just about done here. I'm going to solve this triangle. Solving means you find every side and every angle. Okay, every side and every angle. Well, this is 8 and this is 11. I could find this side a couple ways now. The best way to do is through Pythag still. So 8 squared plus, we'll call it a squared, equals 11 squared. So 64 plus a squared equals 121. Subtract a 64 from both sides, and a squared equals 57. Well, if a squared is 57, then a is just root 57, whatever that decimal is. And if you were actually doing a project where you needed a length, you would do that as a decimal. But if you're just writing down math, save yourself a couple steps and just write root 57. So I found all the missing sides already. Now I need the angles. Well, I'll do tangent. I'm going to call this my angle theta right now. So the tangent of A, tangent of theta, tangent of A, is opposite over adjacent. To get the angle here, I'll do the tan inverse, because tan inverse is how you find angles. And A is going to equal tangent inverse, so second tangent, of the square root of 57, close that parenthesis, and divide it by 8, giving me 43.34 degrees. Now, I didn't have to pick sine or tangent or cosine. I can pick whatever. You know, I could have done, in fact, I probably should have done 8 and 11. I should have done, if this is my angle theta, then I should have done the cosine of theta is 8 over 11. The only reason I say that is because I know these two are correct. I might have made a mistakes along the way there somewhere. So you should always use the ones that you were given with, because they're the ones that we're assuming are accurate and correct. I should have done cosine, or I could have done sine of this angle, but I didn't. I did tangent. Either way, we get the 43.3 degrees. Now that I know that one of them is 43.3, this one down here must be 46.7 degrees, because they're going to add up to 90, because we're in a right triangle. So you can use your Pythag, sine, cosine, or tangent, and inverse sine, cosine, tangent to find everything you need. Here's one more. In this case, we have this angle. And we have this angle, I want to find these sides. Okay, I pick a side I want to find. Which side do I want to find? I'll find this one over here. So I'm going to call this side B. I know that if this is my angle, then this is opposite, and this is adjacent. So the tangent of B, is B over 4. But I really shouldn't have called this capital B. I should have called it 50. I know the tangent of angle 50 is B over 4. Well, I'm going to solve this for B. Tangent of 50, I can just calculate. That's just some number, right? We just pull up the list, grab our calculator. The tangent of 50 is something, so I find it. The tangent of 50 is 1.19. So 1.19 equals b over 4. To solve this for b, I multiply both sides by 4. 4 times 1.19 is 4.76. Side length b over here is 4.76 units. Well, now to find a, I would do Pythag. I could just do cosine or sine or tangent or something. Like I could keep playing with this. I could say, okay, I want to find c. So I could do the sine of 50 equals 4 over c. Now, to solve this, you multiply both sides by c to get rid of the variable on the bottom. So I'd have c times the sine of 50, and remember sine 50 is just some number, equals 4, because these would cancel. Then divide both sides by the sine of 50. So c equals 4 divided by the sine of 50, whatever that is. And you're going to get 5.22. I should say about equal to. C here is 5.22. I could have done that through Pythag also. If I were to do 4 squared plus 4.76 squared, I would get something really close to 5.22 squared, but they'll be a little bit off because there's been some rounding. So if you have this scenario where it's like sine of theta equals something over a variable, these two things end up switching spots. You'd get x equals 3 over sine theta. Same thing. So you can write that a few different ways if you need to. So we can solve right triangles, only right triangles, very simply now with sine, cosine, tangent, inverse sine, inverse cosine, inverse tangent, and the Pythagorean theorem. I'm not going to talk about special rights today. We'll save that for another video. I had some place in here I had a recap though. Recap. Here's our recap. Trig functions allow us to find ratios of two sides. Inverse trig functions let us find angle measures given two sides. Reciprocal trig functions are literally just trig functions flipped over. And then 30, 60, 90s are super important. We'll talk about them more later. Whew, we did it. Trig day 1. Oh, sheesh, that was a long one. I don't know what this guy was thinking talking so much because it's a math video. No one wants to watch math for that long, but people do want to watch this sine wave go up and down and build what's, I guess, kind of looking like a Chinese finger trap here pretty soon. Am I allowed to call that a Chinese finger trap? Is that racist? I don't think it's racist because that's what it's actually called. If you liked this video, please like it. That's a weird sentence. And if you want to subscribe to it, that'd be helpful. Thank you. Share it with a friend. And if you're taking this class, go take your video quiz. Don't forget about that. If you're a teacher who wants to buy the curriculum that's associated with this video, check the description down below. And as always, please feel free to leave me a comment and tell me how awful I am. There it goes.